So I should start out with two disclaimers. The first is that I am not the most qualified person to be giving this presentation. In fact, far from it. Michel himself and several others would be much more qualified. However, someone has to do it, so I will do it. But I might make mistakes about the historical development and so on. So please correct me, Michel. Michel has been a participant in the development of these ideas, unlike me. So the second disclaimer is that this is a pretty diverse audience, and you know, this is a very rich and elaborate sort of edifice of ideas which has developed in the last 30 years or so. And in an attempt to reach this diverse audience, I'm going to take a very global view of things, which means in particular that experts might find this wanting, but let's make an attempt anyway. So I'm going to so here's an outline of my talk. I'm going to start out with with isoperimetric problems in geometry and discuss their connections to curvature. And then I will talk about isoperimetry in probability and ask the question about whether it makes sense to talk about curvature and probability theory as well. And then we will look at various approaches to defining curvature in a probabilistic framework. And if time permits, we will mention another appearance of information-theoretic geometry, but let's see about that. Okay, so let's start with the isoperimetric problem. So here is one formulation. So let M be a Riemannian manifold of dimension n. So I'm going to assume always that my Riemannian manifolds are connected and smooth. So since it's connected, it's a metric space, and with the Riemannian distance providing a metric. And suppose dV is the Riemannian volume element, so you can measure the volume of an open set using that volume element. And let's say that A is nice in the sense that we can measure the surface area of A. So we can define the surface area of A, for instance, in this fashion as the volume of an expansion of A minus the volume of A divided by epsilon, where this expansion of A is the set of all points in the manifold which are within distance epsilon of some point of A. Right? So in other words, you have, let me use the board as well. So you have some set A, and then the expansion of A is something like this, where you look at all points that are within distance epsilon of A. Right? So if this is A, this is the expansion of A. And yes, so this is somehow the rate of expansion. As you expand the set, the rate at which the volume expands, that's a measure of surface area. So you can ask, if we consider all nice sets of fixed volume, what are the sets of minimal surface area? Yes?
Are the British Islands nice set or not?
So this is a
Take the limit and no.
Yeah.
So it's not nice because it's a factor. Boundary is long.
You take the limit when you take this as a definition of the measure of the boundary. Whatever A is nice and not.
Yeah, but it's a famous statement that the boundary is a fractal set, so the boundary is infinite.
Yeah, if it's infinite, that doesn't matter, because I'm asking, if we fix the volume, what is minimizing the surface area? What are the sets that minimize the surface area? Okay, so here are two model examples. So you can look at Euclidean space Rn, for instance. In this case, this is the classical isoperimetric problem, and the isoperimetric extremizers are Euclidean balls. So in other words, if we look at all sets, all Borel sets in Rn, say, which have fixed volume, then Euclidean balls of that volume have minimal surface area, right? Or if you look at the sphere, then the isoperimetric extremizers are spherical caps. So these are, so if you have the sphere, so a spherical cap is, it's just the natural thing, the geodesic ball on the sphere. And those are isoperimetric extremizers. So why is this question important? Well, it's a central geometric question, but it also has many applications to physics. For example, the fact that isoperimetric extremizers in Rn are Euclidean balls explains why soap bubbles are spherical, right? Because they're trying to minimize, there's a fixed volume of air trapped inside the soap bubble, and you're trying to minimize the surface tension, so you have spherical soap bubbles. Okay, so that's the isoperimetric problem, and two examples. So it turns out that curvature plays an important role in understanding isoperimetry. So here is a comparison theorem due to Gromov, which is called the Levy-Gromov comparison theorem. So if M is a compact Riemannian manifold of dimension n at least 2, and you take mu to be the normalized volume element, so this is compact, so it has finite volume, and so you divide the volume element by the volume of M, so this is now a probability measure. Assume that the Ricci curvature is bounded from below. I'm going to mention what Ricci curvature is for those who have not seen it, because I know, as I said, that we have a diverse audience. By some constant k, which is positive, if S is the n sphere with constant Ricci curvature k, so this is just some multiple, some blow up of the n sphere, right? The n sphere of n-dimensional sphere of some radius. Okay, if S is the n sphere with constant Ricci curvature k, and A is an open subset of M with volume of A in M equal to the volume of B in S, B being an isoperimetric extremizer on the sphere, then the surface area of A, of the boundary of A, is at least the surface area of the boundary of B. Okay, so this is saying somehow that if you so before I parse this statement, let me say something about Ricci curvature. So the Ricci curvature tensor is a symmetric bilinear form on the tangent space of M, and it represents the amount by which the volume of a small wedge of a geodesic ball. So let's say you have a geodesic ball in the space, then you look at a small wedge of this geodesic ball and you compare the volume of this to the volume of a similar ball, of a small geodesic ball in Euclidean space. And the Ricci curvature is somehow telling you how these compare. And so it contains less information than the full curvature tensor. But in particular, not surprisingly, the model spaces which have constant curvature are Rn, the sphere, and hyperbolic space. So in particular, the Ricci curvature of the n sphere with radius r is this constant, n minus 1 over r squared. Okay. So what it means to say that Ricci curvature is bounded from below by k is that the Ricci curvature considered as a bilinear form applied to any tangent vector dominates k in the sense of positive definiteness. Okay, so now we can parse the statement. What it's saying is that if you know that the Ricci curvature is bounded below by k, then you can get a lower bound on the surface area of your set in this manifold M in terms of subsets of the sphere. So you can compare with the isoperimetry on the sphere, right? So this manifold has a lower bound on the surface area which is at least as strong as the lower bound on the surface area of a similar set on the sphere. Okay. So there are many other comparison theorems for non-negative Ricci curvature as well. So I'm not going to go through them in detail, but I mentioned the Levy-Gromov comparison theorem. There's also the Bonnet-Myers comparison theorem, which talks about the diameter, or the Bishop-Gromov inequality, and so on. All these say that if you have some lower bound on the Ricci curvature, then you can compare with the sphere of the same constant Ricci curvature. Okay, so the thing to note here is that it's lower bounds on the Ricci curvature which are important, not just the value of the Ricci curvature. In particular, upper bounds on the Ricci curvature do not seem to give anything. So for example, Lohkamp showed in 1994 that if the dimension is at least 3, then any n-dimensional manifold can be equipped with a complete Riemannian metric that has negative Ricci curvature. Okay, this means that this suggests that upper bounds on the Ricci curvature cannot have topological implications, since you can force this on any manifold. So this suggests that these kinds of comparison inequalities would not be possible if you had upper bounds on Ricci curvature, right? So okay. So so let's keep that in mind, that lower bounds on Ricci curvature are important in geometry, and they're related to questions like isoperimetry and so on. And now let's look at the isoperimetric problem in probability. So now I'm looking at Rn for simplicity. Let mu be a probability measure on Rn, and for an open subset A, let's define the surface area with respect to mu as the limit of this thing, where again A epsilon is this fattening of A by epsilon. But now I'm measuring not the rate at which the volume increases, but the rate at which the measure of the fattening increases. Okay, so that's why it's with respect to mu. And then once again, we can ask, if we consider all sets with measure C, what are the sets of minimal surface area with respect to mu? Okay, so measure C with respect to mu. So if this was Lebesgue measure, then we would just be back in the geometric framework that I was mentioning earlier, or if it was the Riemannian volume element. But here we have some probability measure on Rn. So here is one example. If gamma is the standard Gaussian measure on Rn, so the Gaussian measure with mean zero and covariance matrix, which is the identity, that has this probability density function, right? Then the isoperimetric extremizers are half spaces. So this was proved by Sudakov and Cyrelson and independently by Borel. What does this mean? It means that suppose we consider. So remember, this is a probability measure now. So if you consider a half space, actually. So if I consider, if I fix the measure, let's say I fix the measure of a set to be some constant C. This is obviously between 0 and 1. Okay, then there is a, I can look at half spaces with any orientation. So let's say I look at half spaces perpendicular to the first coordinate. Okay, then or hyperplanes perpendicular to the first coordinate. So now I can find the half space whose measure is equal to C, right? There is going to be a unique half space in this direction whose measure is equal to C, right? It's just the probability of this half space under the Gaussian measure is C. And what this statement is saying, that if I if I take any other set with probability C under the Gaussian measure, then among all those sets, this set is going to expand minimally, right? This set has minimal Gaussian surface area. Okay, so this is the Gaussian isoperimetric inequality, and it's very important. It has many implications in probability and also via the closely related concentration of measure phenomenon. It has many applications in statistics, in physics, computer science, and so on. Anyway, so this is a question analogous to the geometric question, but in probability. So so there's also a comparison theorem here, which says the following. So let's first observe that if you look at the Gaussian density, which I'm writing down here, and you look at the log of the density, this is a quadratic function, and so the Hessian of this quadratic function is constant, right? So the Hessian of minus log phi is just the Hessian of this quadratic function, which is just the identity matrix. Okay? So here is a comparison theorem which is due to Bakry and Michel, which says that if mu is a probability measure on Rn with density function of the form e to the minus u, so when I say density function, I mean the density with respect to the Lebesgue measure, of the form e to the minus u, where, so this C2 is not really important, but just for the sake of not worrying about it, we'll say u is C2 and the Hessian of u is at least the identity. So we mean this in the sense of positive definiteness of the Hessian matrix. So the Hessian matrix minus the identity is positive definite. Then if A satisfies that the measure of A is equal to the Gaussian measure of B, measure of A under mu, which is this probability measure whose density function satisfies this condition, then you have a similar comparison inequality for the surface area under mu. Okay, so this is very similar to the Levy-Gromov comparison theorem that I mentioned earlier, except that it is for Gaussian measure instead of for the Riemannian volume element on some manifold. Okay, so and what is it that replaced the condition of curvature? It was this condition here replaces the condition on curvature, the condition that the Hessian of u dominates the identity matrix. Okay, so the fact that its identity is not important, you could put a constant times the identity here. You would just have to take the Gaussian of the same variance, just like, you know, in the geometric setting, if we had a curvature bound of k, you had to take the sphere of the corresponding radius that had that curvature, constant Ricci curvature. So anyway, so what this is very suggestive. It's suggestive that there is so I'm not exactly doing things in historical order, but that's all right. So this is suggestive that there is a probabilistic notion of curvature, and that the probabilistic way of capturing curvature has to do with this Hessian of the log density, right? So so it seems that a lower bound on the Hessian of u for this probability density function e to the minus u has similar effects to a lower bound on Ricci curvature for Riemannian manifolds. So is it possible to build a theory of curvature in probability theory? So this was first done by Bakry and Émery. So they built such a probabilistic theory of curvature lower bounds, but the theory is quite demanding, and I'm not going to describe it in any detail here. But it applies not directly to measured spaces, but to Markov semigroups defined on them. So I'll just mention that that a canonical example here is Brownian motion on a manifold, which is generated by the Laplace-Beltrami operator on the manifold. Or more generally, you can look at diffusions, and so then associated with these stochastic processes, you have semigroups of operators which capture conditional expectations under this process of functions. And if you have such a, so their notion of curvature, of a curvature lower bound more precisely, applies to such semigroups of operators, okay? Or so there are actually there are two authoritative sources for this. One is a survey written in 2000 by Michel, and another is a book written 3 years ago by Bakry-Émery and Ledoux. Anyway, so the picture is the following: that if you have a connected Riemannian manifold, this is one way in which the geometric and probabilistic pictures that I just mentioned get unified. If you have a connected Riemannian manifold which is now weighted, so instead of just looking at the Riemannian volume element, you equip it with a measure which is e to the minus u times the volume element, So it turns out that if you have such a weighted manifold, it's possible to construct this Markov semigroup whose curvature is bounded below in the Bakry-Émery sense. I haven't told you what this is, but let's just take it on faith that it's possible to give this, to say that this has curvature bounded below by k in this sense, if the Hessian of u plus the Ricci curvature of M is bounded from below by k at every point, by k times the identity at every point. Okay, so what plays the role of curvature for weighted manifolds is the Hessian of u plus the Ricci curvature. So now if you specialize to the geometric picture that we discussed earlier, there's u is just 0 because you're just looking at the volume element here. In that case, this is just a lower bound on the Ricci curvature. If you look at the probabilistic picture that I mentioned earlier, where we are looking at a probability measure on Rn, then the Ricci curvature is 0, and this is a lower bound on the Hessian of u. Okay, so this is a way that this quantity simultaneously captures the effect of the geometry and the probability measure. So this object, the Hessian of u plus the Ricci curvature, is now often called the Bakry-Émery Ricci tensor. And there exist several other comparison theorems for it also, providing generalizations of the other theorems that I mentioned in classical Riemannian geometry. So here are some sources. Okay, so in a hidden way, what we have introduced is the notion of a log concave measure, of a log concave density, sorry. So the point is that I've been talking for the last couple of slides about measures of the form, about measures of the form e to the minus u, where Hessian of u dominates the identity, right, or dominates some multiple of the identity. So what does it mean that Hessian of u is bounded from below by something? It means that if this was 0, if the Hessian of u is bounded from below by 0, that would mean that u is a convex function, right? That's just a characterization of convexity for C2 functions. And the fact that it is bounded by some positive constant times the identity says that it is stronger than convex, right? Has some sort of stronger than convexity property. So anyway, so we say that a probability density function on Rn is log concave if the logarithm of f is concave, right? Which could be written in this way: f of a convex combination is greater than or equal to the geometric mean of the values of f at 2 points. So another way of saying this is that f is log concave if f is of the form e to the minus u, where u is convex, right? So this class of densities has been studied a lot. It appears in many places, in convex geometry, for instance, because the uniform density on any compact convex set is log concave. Or you can look at exponential densities, any Gaussian density, and so on. So it's been studied in many areas. And the intuition is that log concave densities resemble Gaussian densities. So for example, functional inequalities that hold for Gaussian densities often also hold for log concave densities or subclasses of them. So now, having seen what we have, about this notion of curvature, it's not that surprising in hindsight that log concave densities should resemble Gaussian densities. There are comparison theorems and so on. Log concave measures are precisely measures on Rn that have non-negative curvature in the sense that we just described, right? So, whereas Gaussians are the ones that have constant positive curvature, right? Okay, so this was all warm up. Now let me talk a bit about more recent approaches to probabilistic curvature. So start with, I want to mention the Brunn-Minkowski inequality, which is one way that one can approach the isoperimetric inequality in Rn with Lebesgue, equipped with Lebesgue measure. So the Brunn-Minkowski inequality says that if A and B are Borel sets in Rn, then the volume of a convex combination of A and B, I have to explain what a convex combination of two sets is, right? The convex combination of two sets is just the set of all convex combination of points where I take the first point from the first set and the second point from the second set. Okay, this is a Minkowski sum or Minkowski convex combination. So the Brunn-Minkowski inequality says that the volume of this Minkowski convex combination is greater than or equal to the geometric mean of the volumes of the two sets. And to see the isoperimetric inequality as a consequence, so yeah, this takes a couple of minutes to see, but it's not hard. It turns out that this form of the Brunn-Minkowski inequality is equivalent to this form, and then in this form, if you take B to be a small multiple of the Euclidean ball, then this implies the isoperimetric inequality, which says that Euclidean balls are isoperimetric extremizers for Lebesgue measure. So note that if you look at this expression, this is looking very similar to the definition of a log concave function, except that the arguments here are not points but sets, right? And instead of a function here, you have a measure here. So you can use this expression to define the notion of a log concave measure. So we will say that a measure is log concave if the measure of a convex combination of two sets is at least the geometric mean of the measures of the two sets. Okay. So I'll actually point out why this is true in a second, but it turns out that if you look at probability measures with densities on Rn, then a probability measure is log concave if and only if it has a log concave density. Okay, so this follows from this was observed by Prekopa, and then a generalization was proved by Borel. I'll come back to curvature in a minute. This is a bit of a digression, but I will come back to curvature. So now here is another way of capturing the Brunn-Minkowski inequality. If f, g, and h are non-negative functions on Rn, which are integrable, and for a given lambda between 0 and 1, they satisfy this condition that the h of a convex combination of 2 points is at least the geometric mean of the values of f at the first point and g at the second point. Okay, this looks extremely mystifying the first time you see it, if you have not seen it before. I mean, I know I found this very mystifying the first time I saw it. Then the integral of h over Rn with respect to Lebesgue measure is at least the geometric mean of the integrals of f and g. Okay, so I'll try to make this a little less mystifying with some comments. So the first thing to note is, suppose you take the following example, take f, g, and h to all be indicator functions of sets, okay? But f is the indicator function of a set A, g is the indicator function of a set B, and h is the indicator function of lambda A plus 1 minus lambda B, this Minkowski convex combination, okay? So this trio of functions satisfies this hypothesis. Why is that? Because, I'm looking at here, so with this choice of functions, what do I need to check if this inequality is satisfied? These functions only take the value 0 and 1. So I only need to check when the right-hand side is 1, because otherwise this is 0. If this is 0, then this is always true, because this takes only value 0 and 1. Right? So when is the right-hand side 1? It's 1 only if both f and g are 1. But if both f and g are 1, then x is in A and y is in B. But if x is in A and y is in B, then lambda x plus 1 minus lambda y is in lambda A plus 1 minus lambda B, which means this is also 1. So the hypothesis is satisfied for this trio of functions. And if you plug in this trio of functions, you see that the integral of the indicator function is just the volume. So this is saying that the volume of this convex combination of sets is greater than or equal to the geometric mean of the volumes. Right? So this is exactly the Brunn-Minkowski inequality. So this inequality, the Prokopov-Leindler inequality, can be thought of as a functional version of the Brunn-Minkowski inequality. Another way to try to parse this is to see it as a reversal of Holder's inequality. So Holder's inequality gives a lower bound on this right-hand side here in terms of this integral. But now we have an upper bound in terms of the integral of h. And this is, here I wrote down, given f and g, what's the best h that I can construct that satisfies this condition? It's going to look something like this. Okay, so you can think of it as a kind of reverse Holder's inequality. Okay, so the Prokopov-Leindler inequality, once you have it in hand, it's extremely useful. So here is one very quick implication. If f, g, and h satisfy the hypothesis of Prokopov-Leindler inequality, this hypothesis, and u is a convex function, then f e to the minus u, g e to the minus u, and h e to the minus u also satisfy the hypothesis. Because if you just plug in h e to the minus u, etc., just by convexity of u, that extra term, you're just multiplying two inequalities here and to verify this. Okay. So, but if this trio of functions verifies this, then now I have a new conclusion using this trio of functions. And that conclusion can be rewritten as saying that the integral of h d mu, so now this is really the integral of h e to the minus u with respect to Lebesgue measure, but that's the same as the integral of h d mu, because e to the minus u Lebesgue measure is just d mu, right? So this is saying that the Prokopov-Leindler inequality holds not just for Lebesgue measure, but for any measure with a log concave density. Right? As long as you have a measure mu whose density is of the form e to the minus u with u convex, then the same conclusion, the same inequality holds, replacing Lebesgue measure by this measure mu in the conclusion. Okay. In particular, now if we specialize again to indicator functions of sets, you see that any measure with a log concave density is log concave. Right? Because now if you specialize to indicators of sets, this is talking about the measure of A, the measure of B, the measure of the convex combination. Okay. So actually the Prokopov-Leindler inequality also gives us a way to measure curvature. So why is that? Because suppose now mu is a probability measure on Rn, which is not just log concave, but stronger than log concave, right? So the density of the form e to the minus, I don't know why I switched notation here. Let's imagine this is u, e to the minus u, the Hessian of u greater than or equal to some constant. Then it turns out that you can get the same conclusion with a weaker assumption, with a weaker hypothesis on the functions f, g, and h. Okay, and that's natural because I have a stronger hypothesis on the measure here, namely that, let's say this is positive, okay, so it doesn't matter. I mean, this is weaker if C is positive, this is stronger if C is negative. So, okay, so the point is that you can interpret this in terms of curvature, because again, one can specialize to indicator functions and get conclusions for, so what is so one should draw a picture to understand this. So, if you're looking at Rn, let's say I have two sets A and B. Okay, I'm just drawing it this way so that we can see geometrically what Minkowski convex combinations look like. So if I look at a Minkowski convex combination of these two sets, it's going to look something like this, right? So maybe I should. So if I'm drawing two sets of similar shapes so that I can see what the Minkowski convex combination looks like. Okay, it's going to be, if you draw sort of geometrically, it's going to have this kind of shape, right? Now, if you have positive curvature, if you did this on the sphere, for instance, what would you expect to see? You would expect to see that this Minkowski, the natural, if you look at geodesics now, and you look at instead of looking at lambda of the way along each geodesic, along each straight line, you look at lambda of the way along each geodesic, then you are going to get some larger set, right? That's what positive curvature is going to give you. And this inequality is saying something similar. It's saying that with a weaker assumption on these indicator functions, you can get the same assumption. So somehow some smaller set already has at least this measure. So that's like an expression of positive curvature. Okay. So.
Sorry, could you repeat that?
So okay, I'm waving my hands a lot, but you can. So you are getting a similar conclusion, right?
I get that.
Yeah. So but this is one. But applying it to indicator functions, you can.
My doubt is with the geometrical interpretation. So,
yes.
So I see that you made a stronger assumption on the density, so you can weak the hypothesis on the inequality functions.
Yeah. So I'm waving my hands, but what I want to say is that this is kind of expressing this kind of picture, right? That you have a larger measure for this interpolating set than you expected from the zero curvature case. Right. Here you're kind of, well, anyway, I don't want to spend too much time on this, but you're right, I'm waving my hands. So, okay. So this is stated for Rn, but it turns out that this can be extended to weighted Riemannian manifolds under a lower bound on this Bakry-Émery-Ricci tensor that I mentioned. This was done by Cordero, Makan, and Schmuckenschlager. Okay, so also also around the same time, Cordero, Makan, and Schmuckenschlager, as well as so there's a bunch of papers around the same time which noticed that these kinds of that curvature can also be captured using properties of the relative entropy. So what is relative entropy? So how am I doing on time, by the way? Okay.
20 minutes.
Yeah. Good. So suppose M is some space equipped with a reference measure L, and suppose probability measures mu and nu have densities F and G with respect to L. Then the relative entropy between mu and nu is defined like this. So I'm abusing notation here. The relative entropy between the measures, I will also write that as the relative entropy between the densities. That's defined as the integral of f log f over g taken with respect to L, with respect to this measure L. Okay? So if you have seen, so I was, based on conversations at dinner yesterday, some people have not seen relative entropy, which is why I'm recounting this definition. So for any mu and nu, the relative entropy between mu and nu is non-negative with equality if and only if mu equals nu. So this follows from Jensen's inequality. It's actually very simple. So you can write that as the expected value of log f over g, right? Where the expected value is taken using the density f, okay? This is the same as the expected value of minus log g over f. But minus log is a convex function, so this is greater than or equal to minus log of the expected value of g over f. Okay, but this is the integral of g over the support of f. This has to be the integral of g is 1 over all of Rn. So this is over all of m. So this is at most 1, which means this is greater than or equal to 0. Okay, and it's not hard to check that this is equal to 0 if and only if mu equals nu. So this is a very useful notion of distance between probability measures, but it's not a metric, right? Because although it is non-negative and it's equal to 0 if and only if you have equality, it's not symmetric, right? And it doesn't satisfy a triangle inequality of the type that you want for metrics. So, but one reason it's useful is because it dominates several of the usual distances that people consider on the space of probability measures. So for example, one has Pinsker's inequality, which says that if the total variation distance between mu and nu, which is defined as the L1 norm of the L1 distance between the densities, then the total, so the total variation distance squared is bounded by twice the relative entropy. Okay, this means that if the relative entropy between, if a sequence of probability measures mu n converges to nu in the sense of relative entropy, then certainly it converges in this total variation sense. And this convergence in total variation is much stronger than convergence in distribution or weak convergence. So this is a very strong notion of convergence. Okay, so here's another distance on the space of probability measures. It's called the Wasserstein distance. So suppose M is a metric space with a metric D, and we have probability measures mu and nu on M. Let C of mu nu be the set of all couplings of mu and nu. What do I mean by couplings? This is the set of all probability measures on M cross M with first marginal mu and second marginal nu. Okay, so what do I mean by this? For those who are not who don't see these terms all the time, what I mean is the following, that so let's say, so pi is a coupling of mu and nu. If so pi is a probability measure on M cross M, where mu and nu are probability measures on M, right? But so what I mean by marginals is to say that pi of, if you look at some subset of M cross the whole set, okay, this is equal to mu of A. So this is what I mean by saying that mu is the first marginal, and pi of M cross a subset of M is equal to nu of B. This is what I mean by saying it's the second marginal. Okay. So this is a joint probability distribution with marginals mu and nu. Okay, so those are couplings. So for example, a trivial coupling is given by the product measure, right? When you take sort of independent random variables distributed according to mu and nu, that gives you a trivial coupling. Okay. So the Wasserstein distance between mu and nu is defined in this way. You take the infimum over all couplings of the expected distance squared between x and y. So this is just a metric on M. You look at the distance between x and y squared, and you take the expected value using this coupling pi, okay, which is some measure on M cross M. So this makes sense. Okay. So So this has nice interpretations in economics, for instance, which is where these kinds of distances first came up. Because it can be thought of as the minimal cost of transporting material from a configuration. Let's say you have some, sand or something like that, which is distributed. You have some sand dunes on the beach, which are distributed according to distribution mu, and you want to change the configuration to distribution nu. Okay, the mass is the same. You just want to move the sand around so that it has a new shape. Then this is the sort of minimal cost of transporting the sand if I'm paying this much to transport 1 unit of sand from X to Y.
How is it related to Monge-Cantor, which
yeah, so so there's a whole, yeah, so it's the same kind of thing. So there's a whole bunch of them. Different names are used. And you can also use here, instead of taking the square of the metric, you can take pth powers, or you can take the first power, and then it becomes, Monge-Cantor. So, but yeah, I mean, these are all related distances. Yes.
For the anecdote, Wasserstein, who's still alive, by the way, he's working in algebra, and he only wrote one paper on Wasserstein distances. But these distances were known before by Moore and Cantor, which should be reminded.
Thanks. So, okay, so so this is a metric on the space of probability measures with finite second moment. So there are remarkable results of Brenier and McCann, which say that if mu and nu are nice, for example, if they are absolutely continuous with respect to Lebesgue measure or something, then you can relax the condition on one of them. Then the optimal coupling has a particularly nice description in the sense that it's actually degenerate in a sense. So if you think of these as, if you think of the random variable, so you have a pair of random variables x, y, which is distributed according to pi, right? This is your coupling. Then, x has distribution mu and y has distribution nu. That's what it means that it's a coupling, right? If x, y is distributed according to pi, then x will have distribution mu and y will have distribution nu. But what these results of Brenier and McCann say is that the optimal coupling is actually one where y is a function of x. And not just any function, but the gradient of a convex function of x. Okay, so this is an absolutely remarkable result. And once one has this result, it allows for an infinitesimal, it allows for thinking of the Wasserstein distance as the geodesic distance between two probability measures. And it allows for constructing geodesics in the space of probability measures, okay, at least if they are reasonably nice, okay. So in particular, so I'm not going to describe this in more detail because it would take too much time, but I know that, for example, you will see more of this in talks to come. So in particular, one has, so one can define an interpolation, which is called the displacement interpolation, mu sub s, with s in 0, 1, such that mu sub 0 is mu and mu sub 1 is nu. And these are sort of geodesics for this Wasserstein distance. Okay? So the Wasserstein distance between mu and nu is just the length of the geodesic between mu and nu. Okay. Okay. So now with these two notions at hand, one can define this notion of displacement convexity. So let mu sub s be this displacement interpolation between mu and nu, right? So one interpolates in this Wasserstein sense. Then a functional E on the space of probability measures is k displacement convex if you have this kind of condition holding true that this is, what is this? If k was 0, that's what this statement is saying. If k was 0, this is just saying that E is convex. E of mu s is a convex function in S, right? That's what this is saying if k were 0. right? So this is somehow the deficit, the convexity deficit, and it's saying that the convexity deficit is dominated by some factor times the Wasserstein distance between mu0 and mu1, okay? So if this condition is satisfied by this functional E, then we say that the functional E is K displacement convex. And with this in hand, we come to this information-theoretic geometry of metric measure spaces. Well, this is the first step, is that if you take a Riemannian manifold with Riemannian volume M, then the Ricci curvature is bounded from below by K if and only if the relative entropy with respect to M, let's say it's normalized, is K displacement convex on the space of probability measures with bounded second moment. Okay, so so this was proven by von Rennes and Sturm, building on, well, maybe independently of so this particular result was proved by von Rennes and Sturm, but there are also weighted versions of this result replacing the Ricci curvature by the Bakry-Émery Ricci tensor, and here you don't use M, but you use your measure on the manifold, right? Weighted measure on the manifold. So so far this is a very nice statement. It makes sense in this geometric framework. But the thing to note here is that this entropy condition above, which is equivalent to lower bound on the Ricci curvature in a geometric setting, uses only the metric structure, because if you look at the definition of displacement convexity, so the only thing that I used was the notion of relative entropy, which does not care about the metric, which does not care about it just cares about the sigma fields, not about the metric per se. And the Wasserstein distance depends only on the metric in the sense of metric space, not the metric in the sense of Riemannian metric, right? So the point is that this only uses the metric structure. So you can now say that for any metric space equipped with a measure, which we will call a metric measure space, okay, we will say that it has Ricci curvature bounded from below if this property holds, that the relative entropy with respect to this measure on the metric space is K displacement convex in this sense. So the question is, is this a sensible definition? And this is what was shown by Sturm and Lott and Villani in a celebrated trio of papers. So what did Sturm and Lott and Villani do? They extended the notion of curvature lower bounds via displacement convexity of relative entropy to a general class of metric measure spaces. They proved closure properties. So one of the reasons that people were interested in these things were to say things about spaces that don't have Riemannian structure, that are singular in some way. And they proved these closure properties under appropriate notions of convergence on the set of metric measure spaces with a given curvature lower bound, which means that you can deduce things about singular spaces from sequences of Riemannian manifolds, for instance, which converge to them in an appropriate sense. So finally, this provides a synthetic notion of curvature for metric measure spaces without demanding the infrastructure of these Markov semigroups and so on. And in fact, mimicking curvature dimension conditions that Bakry and Emery came up with in the diffusion setting, they also developed more complicated curvature dimension conditions which capture not just curvature but also dimension for metric measure spaces where it's not obvious what dimension should be, right? Unlike for Riemannian manifolds, for instance. So more recently, a number of works have noted that there is actually some equivalence between these curvature conditions of Bakry-Émery type and this Lott-Sturm-Villani type. Okay. But anyway, so all right, how am I doing on time? 5 minutes, 2 minutes, yeah. So maybe I should skip the other appearance of information theoretic geometry and just jump to the concluding remarks, which is, so I wanted to show why notions of curvature are closely related to isoperimetry, and I didn't really say anything about concentration in both geometry and probability, and that while one framework for curvature lower bounds was provided by Bakry and Emery, this more recent framework of Lott, Sturm, and Villani is very powerful and applies to the setting of metric measure spaces. And it relies on this convexity property of the relative entropy functional. That's all I wanted to say. Thanks.